To any space you're interested in, you can associate a group called its fundamental group. The fundamental group keeps track of how many essentially different loops there are in your space. So here's a space, this black circle in the picture, and by a circle I really mean the black boundary of the disk, so I'm not thinking about the white interior of the disk. And here's a loop that lives on that black circle. I'm going to start at this point here. It's going to be my base point. I'm going to move around the circle anti-clockwise, because that's what mathematicians do, around until I get back to the start point. That's a loop. I'm going to call that loop A. And so here is an essentially different loop from A. I'm going to call it B, and it's going to be in blue. Unfortunately, I can't draw it on the circle anymore because the circle's one-dimensional. I've already drawn something on it, so I'll draw it slightly inside the circle, but imagine it's really on the circle. So I'm going to start at the same point, same base point, and move around the circle. And when I get back to the base point, instead of stopping, I'm going to keep going, because I'm crazy, all the way back to the base point again. I'm going to call that loop B. So I claim these two loops are essentially different. They will define different elements of the fundamental group, because A goes around once and B goes around twice. In fact, in this example of the circle, the fundamental group is going to turn out to be exactly the group of integers under addition. That's basically because a loop can go around the circle, coming back to its start point, any number of times, and that number is all that really matters about that loop. The group structure here, in other words, the fact that you can add two integers, is just the fact that you can go around one loop and then round another loop, and the concatenation of those two loops is a third loop. In this case, if we concatenated A and B, we'd have this crazy loop C, which is going to do purple, which would go around once, twice, 3 times. I can count, okay. So this is a very simple idea, but the key difficulty in it is making precise what we mean by two loops being essentially the same or essentially different in the fundamental group. So let me, before I make that more precise, give you an example of two loops which I really think of as being the same in the fundamental group. So here's our circle again. Here's our loop A from the previous slide that just goes around, starting at the base point, coming back to the base point. And I now want to give you a different loop which I consider the same in the fundamental group as this loop. So I'm going to draw it in green. Apologies to those of you who are colourblind, but remember these are supposed to be essentially the same in the fundamental group, so it doesn't matter if one is green and one is red and you can't tell the difference. Okay, so it's going to go around much the same as A, but then when it gets halfway around it realises it's forgotten something, turns back on itself, goes quarter of the way back, then realises it's okay, and comes back around and finishes back where it started, at the base point. So these two loops define the same element of the fundamental group. And the way we see this, the way we define this, is that we say there's actually a one-parameter family of loops that interpolates between the green guy and the red guy. And a representative example of one of the loops in this one-parameter family would be this purple loop that goes like the green loop. Forgets something, goes back, but doesn't have to go back quite as far to pick it up, and then keeps going right back to the beginning. And you can imagine that detour taking less and less time, going less and less far around the circle, and having a whole one-parameter family of loops that interpolates. So even further along that one-parameter family, maybe you only go back a very tiny amount, until eventually you get to the red loop that doesn't go back on itself at all. So such a one-parameter family of loops is called a homotopy of loops, and in a second I'll make that into a precise mathematical definition. So first of all, what exactly do I mean by a loop? Well, let's suppose we're talking about some general space M. Maybe you just want to think about the circle, like on the previous slides. And let's fix a point, little x, in M. So a loop in M based at x is a continuous map, maybe called A, from the interval between 0 and 1, in other words the numbers between 0 and 1, to the space M, and it needs to satisfy some conditions. So first of all, it's supposed to be based at x, right? So it's a map from the interval, which means every point in the interval gets mapped somewhere in M, and we know the start and end points are supposed to go to the point x. So those two conditions would be that A of 0 equals x and A of 1 equals x. So this is the base point. And the other key property that we need A to have in order for it to really correspond to what we think of as a loop is that A is continuous. If it's not continuous, it could be something horrible. It could kind of go around halfway, jump in space-time through to a different point in M. Like, it could, let's do it in blue, where it could kind of go around, jump down here and start going around this way, and then jump over here. And again, it could do anything like this and then end up back at x. That's discontinuous. We don't want that at all. We want it to be a nice continuous loop. That's what we mean by a loop. So now I want to tell you what it means for two loops to be the same in the fundamental group. So there's a technical name for this. And that technical name is homotopy. So we say that two loops are homotopic if the following condition holds. So let's say one of the loops is A0. Maybe that's this one. And one of the loops is A1. And that's maybe one of these funny ones that jumps back on itself and comes back like this. Okay, so we've got two continuous maps from the interval to M based at x. And what we would like is for there to be a family, like in this previous example, of loops, maybe AS, which interpolate between these two guys, between the red one and the blue one. And there's a whole one parameter family of these as this parameter S varies, maybe also between 0 and 1. So we get lots and lots of these purple curves in between that go around less and less and less. Actually, in this example, they go around more and more and more. Right, we start off with this red curve that just goes straight around, and then we start to deviate more and more until we become this blue curve that's now hidden behind all these purple guys, that goes halfway around, detours back up, and then comes back down to x. Okay, this is what we mean by a homotopy, but to be precise, I'm going to have to tell you what it means for this family AS to depend continuously on S. The easiest way to say that is, well, okay, look at this picture. What I've actually defined is a map from the whole square, this thing I'm colouring in purple, into M, our space. Let me call that H. H stands for homotopy. Sorry that there's a proliferation of letters now. So H is a homotopy between A0 and A1. Exactly what that means is that each S gives us a path AS depending on T, and that path AS depending on T is really just H of ST. Right, so you pick a point somewhere, let me do it in black maybe, you pick a point somewhere on the square that lives at some S coordinate that tells you which of these purple paths you're supposed to use, and it lives at some t coordinate, and that tells you how far along the purple path you're supposed to go. That gives you a point in M. That's what this homotopy H does. There are going to be some conditions, but those conditions are kind of implicit in this picture. So let me just say what they are. First of all, along this red edge here, that is the edge s equals 0, the path h of 0, t should agree with the path a of 0. So let's write something. A of 0 of t, sorry for the switching colour, is going to be h of 0, t. Similarly, along this blue edge at the right hand side, that is at s equals 1, we need a1 of t to be h1 of t. In other words, this homotopy goes between the loops a0 and a1. And what about the other two edges in this picture? Maybe I'll use green now. So the top edge and the bottom edge of this picture, what do they correspond to on the right hand side? Well, that would be the points h, s, 0 and hs, 1. In other words, that's the points as of 0 and as of 1. In other words, it's the base points of the purple paths. And they're all based at this point x. So actually hs0 and hs1 both equal to x. So this whole green edge at the bottom and the whole green edge at the top map just down to this one point, this green point called x. Okay, so a homotopy between a0 and a1 is a map from the square, a continuous map from the square that satisfies these four boundary conditions that I've written here, here, and here. The key thing here is that H is a continuous map from the square. That means that it depends continuously on both S and T in some compatible way. So it's high time for an example where I actually compute the fundamental group of something for you. And I'm going to take the simplest possible example, which is just Euclidean space. Okay, I'm going to work in n dimensions. If you don't like that, you can just imagine this is R2, the plane, two-dimensional space. Let's suppose I've got a loop, and let's pick our base point to be the origin 0, 0, or 0, 0, 0, 0, 0, if you're in n-dimensional space. And let's take a loop. Based at 0, just some random path. It can do whatever it wants, as long as it comes back to 0. My claim is, no matter which loop we picked, let's call it A, this guy will be homotopic to any other loop. In particular, it's going to be homotopic to the stupidest loop of all, which is just the loop that stays where it is for all time. So let's call that loop B. So what is this? This is the constant loop. B of t equals the point 0. Remember, this 0 means the origin in Rn. Okay, what's the proof? It's very easy to prove. I can just write down a homotopy. Okay, I need a one parameter family of paths that starts at A and ends at B. The parameter is this S. So all I need to do is to take the path A of t and multiply it by S. This makes sense because A of t is a point in Euclidean space. I can rescale it by any number, in particular by S between 0 and 1. If I rescale it by 1, so when S is 1, I just get A again, because multiplying by 1 doesn't do anything. If I multiply by 0, so at S equals 0, then all the points get mapped down to the origin. So you can see that h of 1 comma t is a of t, h of 0 comma t is b of t, and you can also see what happens at h of s comma 0 and 1, because all of these paths start and end at 0. Right, if I just substitute in 0 in this expression up here, a of 0 is 0, a of 1 is 0, so these two boundary conditions, hs of 0 is 0 and hs of 1 is 0, are satisfied. This proves any loop in Rn is homotopic to the constant loop. So this says the fundamental group of Rn, which is the group of all loops considered up to homotopy, is just the trivial group. There's only one element, represented by, for example, the constant loop, but also by any other loop. So let's now do an example which is non-trivial, as in it will give us a non-trivial group as the answer. So let's start with the circle. The circle is the simplest space that has a non-trivial fundamental group. I've already told you what the answer is in the first slide, right? It's the integers. But let's try and get the rough idea of how you might prove that. So, okay, if I've got a path like the one we started looking at that just goes around the circle once, then you might detect the fact it goes around the circle once in the following way. You look at the angle, let's say phi of t, that goes between this horizontal line and the line that joins the centre of the circle to the point a of t at time t. If you want to think in terms of complex numbers, maybe a of t is the point e to the I theta of t on the unit circle in the complex numbers. And as t goes from 0 to 1, we can see theta of t is going to go from 0, it's going to increase. By the time you get halfway around, it's at pi if we're working in radians. We keep going, and over here it's 2 pi radians, 360 degrees. So now theta of 0 is 0, but theta of 1, instead of being 0, is 2 pi. So although we got back to where we started in the space, the angle, or the argument, has changed by 2 pi. So if you've seen, taking logarithms in complex numbers, this is exactly that kind of phenomenon that you get, where the argument jumps by an integer multiple of 2 pi. So we can actually use this idea to show that the fundamental group of the circle is the integers. What I'd like to draw now is a graph of how the angle changes as we go round this red loop, our favourite loop that just goes around once. Okay, so here's a graph of the angle theta against t, and maybe this is height 2 pi. Okay, so as we start at time 0, the angle is 0, and at time 1 we know the angle is 2 pi, and in between we just increase straight line slope from 0 to 2 pi. As we move around the circle, the angle just increases. Right. If we had been the loop that went around twice, this graph would have looked slightly different. It would have instead gone around all the way to angle 4 pi. It would have had to go twice as fast, and the graph would look something like this. It's supposed to be 2 pi, sorry, 4 pi. If we'd had one of these silly loops that doesn't know where it's going, it would have gone round part way, so maybe at some point it would have reached an angle pi, but then it would have gone back on itself. So it would have followed this line here and then started going back on itself and then turned round and kept going, and it would have still traced out an angle 2 pi at time 1. So you can see, okay, these two loops, this red loop and this purple loop, are essentially the same. They're homotopic. And the graphs of the angles look more or less the same in the sense they start at 0, 0 and they end at 1, 2 pi. Whereas this other loop ends at 1, 4 pi. Okay, so the way we're going to prove that the fundamental group of the circle is the integers is we're going to define for each loop a number, which is this increase in the angle as you go round that loop. And it's always going to be an integer multiple of 2 pi because we know that if you go round the circle and get back to the same point, you've gone round some definite number of times. So here's what we need to prove. Given a loop, I consider the associated angle as a function from the interval into just the real numbers. What I need to show is that if two loops have an angle function that starts at, say, 0, 0 and ends at 1, 2 pi n for an integer n, and that's the same integer for the two different loops, then those two loops are homotopic. And I need to show that if I have two homotopic loops, then the angle functions they define start and end at the same points. In other words, they start at 0, 0 and end at 1, 2 pi n for the same integer n. Okay, so here I'm going to prove the first of those two things. Suppose I've got two angle functions defined on 0, 1 that both start at 0, 0 and both end at time 1 at a height 2 pi n for some fixed integer n. Okay, so one of them I'm going to draw in red. Maybe it's this, some loop that does go back on itself a bit, and maybe the other one I'll draw in blue or green. Okay, so this is going a bit further, then back on itself. Maybe even negative angle, that's possible, right, if it goes back far enough. But it ends at time 1 at height 2 pi n. How do I prove these two loops are homotopic? Well, remember we had a trick that worked for Rn, right? For Rn we just sort of squished everything to the origin with a homotopy that was just rescaling. And we're going to do something pretty similar here, right? So there's an obvious loop which moves around at a constant speed, this black loop. And all I have to do is, squish the graph down continuously of this green guy, or up, depending on whether it's below or above this green line. And I get a way of squishing the green line onto the black line. And I can do exactly the same for the red line. It's going to get difficult to see, so maybe I'll do this in red. Right, if it's below, I squish it upwards. If it's above, I squish it downwards. Okay, that will define me a homotopy from the green curve to the black curve, and from the red curve to the black curve. So both the green and the red graphs are homotopic to the black graph. If I look at what happens to the loops, the corresponding loops in the circle, sorry, I'll do the circle in black. I don't seem to be able to delete it very easily, so let me just draw over it. Okay, so there's my circle. This red loop is kind of wiggling to and fro, And as I squish it down towards the black loop, those wiggles are just getting smaller and smaller. Similarly with the green loop, it starts off with some pretty enormous wiggles. And as I squish it down onto the black loop, those wiggles become smaller and smaller until it just becomes the black loop that goes around with constant speed. So if two loops start at angle 0 and end at angle 2 pi n for the same integer n, then they're homotopic. It's actually harder to show the converse direction, that if two loops are homotopic, then they define the same integer n. Or rather, well, it's not that difficult, but it involves a lemma called the homotopy lifting lemma. So let me explain the idea. So let's suppose we have our graph. Okay, at time 0 the angle is 0, at time 1 the angle is 2 pi n. And we've got some path, let's make it red. Boop, 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 boop. What I would like is to be able to say that as I homotop the path through a family, let's say AS, like we had before, I can also homotop this graph. Intuitively that makes sense, right? The angle, the path in the space of angles should change in a nice continuous way as you vary the path. This statement is true. It's called the homotopy lifting lemma. It requires a bit of work to prove it. Once you have that, actually the proof is not so difficult, because if you've got a homotopy now, the graph of the angle function changes continuously, which means in particular the value of the angle function at time 1 changes continuously. But it has to take on the value 2 pi times some integer, so it can't jump from one integer to another integer. That's a sketch of the proof. If you want to understand it better, then you should probably look in a textbook on topology about the homotopy lifting property. So let me write that down. This uses what's called the homotopy lifting lemma. So in conclusion, what have we proved here? We've proved that if A0 is homotopic to A1, actually I like to write homotopy this way as a kind of squiggly equal symbol. So if A0 is homotopic to A1, then the graph of the angle function, let's say theta 0 for A0, jumps by the same amount that the graph of the angle function, theta 1 jumps. Sorry for the palimpsest that's this slide. So okay, does this make sense? So what I'm saying is A0 is homotopic to A1 implies that the difference between the angle of A0 at time 1 and the angle of A0 at time 0 is the same as the difference between the angle of A1 at time 1 and the angle of A1 at time 0. Okay, so this fact, together with the fact on the previous slide, shows that the fundamental group of the circle is the integers. Finally, I haven't really talked much about the group structure, but hopefully it's clear that if you have two loops, like this one and this one, we draw arrows on them to show that they have a direction. Then you can get a third loop by going around this one and then around this one. This is called concatenation of loops. It defines as some sort of group structure on the fundamental group. The inverse of a loop, for example, right, if we have a group, every element has an inverse, is the loop that goes backwards around the same path. And how can we see this is an inverse? Well, let's suppose we go round this and then round its inverse. We get a loop that looks like a croissant, maybe, I don't know. And we can homotop this back to the constant loop by just going part way around and then coming back. Right, we get a one parameter family of loops this way. I should have probably said first, the constant loop at the base point is the identity element of the group. Associativity is a little tricky to check. I'm not going to talk about it here. What I'd instead like to say is that we've seen two examples of the fundamental group in this sequence of slides. The first it was trivial, in the second case it was the integers. And of course, most of the time the fundamental group is something extremely complicated. So I just wanted to finish with an example where the fundamental group is something really big and non-abelian. So let's take the plane, right? So this slide is the plane. And let's cut 2 points out of the plane, these 2 points. I claim that the fundamental group of the plane minus these 2 points is the following group. It's called Z star Z. It's the free product of the integers and the integers. What does this mean? Well, it means if I write an A here, so A is a generator of this copy of Z and B is a generator of this copy of Z, then the integers star the integers is the group of all possible words that I can write using A, B and their inverses. So something like this would be an element of this group. And A and B are not allowed to commute with each other in this group. So I just want to convince you that this, this group should have something like this structure. So here's the loop A, here's the loop B. Doesn't matter which way I go around. So if they're not supposed to commute with one another, that means that if I do A and then B and then A inverse and then B inverse, the loop I get should not be homotopic to the constant loop. Okay, I'm not going to prove this for you, but I encourage you to get 2 pencils, stand them upright, like here and here, get a piece of string, wrap it around the pencils in this configuration, and then see if you can undo it without lifting it over the pencils. And I guarantee you won't be able to do it. The reason is because this purple thing I've drawn is the word A, B, A inverse, B inverse in this fundamental group. And because this group is not abelian, A and B don't commute with each other, you can't just pull this A past this B and cancel with this other A. This path you may have seen before if you've done a course in complex analysis. It's called the Pochhammer contour, and it's used in some evaluations of the beta function. You do some integral around this path to find the value of some complex analytic function. And actually this whole subject of fundamental group really started in complex analysis. People looking at paths that go round poles of functions, holomorphic functions. that's somehow the origin of a lot of topology, actually. But that's maybe a story for another video.